Okay, so we have an example problem from supplemental that says we're trying to find the volume of a solid whose base, this is different from revolutional volumes, okay, is bounded by the graph y is x plus 1. So let me go ahead and graph this. First of all, these are cross-sectional volumes, so it is three-dimensional, something that I want you to develop. It's a little weird when you first do it. I did it in college, but you can do it in high school. Is you have y and an x-axis, and you're going to look at this from like a different perspective. You're going to look at it because now we have something called the z-axis, and it goes down below the paper, if you will. Okay, can you visualize that? Okay, so it's like you're over here, just floating in the sky, and you're looking down on this, and like here's the ground, if you will. There's the ground. You see that? And I had trouble looking at it, and then it'd be solid again. So there's a plane here. Think of it as there's the ground, and it's the x and y Cartesian plane just laying on the floor. I don't know, just on the floor like here in class. Okay? Can you visualize it now? Now I'm going to go ahead and draw what these functions look like, and we're going to do it like this. The blue one is x plus 1. Remember, this is lying on the ground, so you got to think of it almost three-dimensionally. Not almost, you have to think of it three-dimensionally. And there is x plus 1. Whoops, my bad. Shifted how many units up? 1. So this is actually x plus 1. We're looking at this three-dimensionally. Now, if I'm going to graph x squared, let's do this in orange. X squared minus 1. Here we go. I'm looking at this two-dimensionally now. It's going to look like this. You with me? And go ahead.
Isn't it -1?
Oh, minus 1. Oh, thank you. So shift what?
Down.
Down 1. And in orange. There we go. Cool. So far, so good. Now, with the indicated cross sections as perpendicular to the x-axis, and we have all these different shapes. First of all, I've just found my area, right? I've just found my cross-sectional area. And guys, when you do your homework, some people develop really, really outstanding notes when they're doing this, and I would definitely say take your time when doing it, because it doesn't matter how fast you go with these problems, you're wrong at the very beginning. Okay? So here's my area. Now I'm ready to show these cross sections of squares. Now this is big, what I'm about to show you. These are cross sections of squares. I need to first think that if I integrate area, I get volume. And because of that, I have to come up with an area that represents the area of a square. What's the area formula for a square? I prefer not base times height, I prefer what? Side squared. Okay? So the area for a square is side squared, and guess what we're going to have to solve for as far as calculus-wise of top minus bottom? The side. You with me? So we're basically going to integrate side squared, and we're either going to do it dx-wise, or we're going to do it dy-wise. Okay? So this is important. This is huge. Perpendicular to the x-axis. That means it forms a 90-degree angle with the x-axis. Is that dx slices or is that dy slices? These are dx slices. Because if here's my x-axis and here's my y, and I have things that are perpendicular to the x-axis, look at that. Those are vertical slices, which are dx. You with me? Alright, so we're going for something that looks like that. Now let's go ahead and develop a drawing, just so you can visualize what's going on. And I'm going to put the base of these shapes, let's put the base in black, okay? And then we're going to have them come out in green. Here we go. So the base, let's pick something in the middle. That could be the base of one of the squares. In that same distance that I just showed that base, I have to come up with that, because the area formula for a square is side squared. Do you see how this just came out of the page? Okay, and if I were to shade this, let's shade it very methodically, it just created that square that just popped out of the page. Yeah.
So wait, where's the origin of the parabola? Because I thought it'd be at 0, -1, but it doesn't look like that on the graph.
The origin of the parabola?
Yeah, of the orange.
The vertex is at 0, -1.
Okay.
But that's not the origin of the integral. The integral is going to be integrated from this x value all the way to whatever that x value is right there.
Yeah, but why is it like looking like that? Is that just you drew it weird? Or?
I'm drawing it three-dimensionally.
Oh, okay.
Okay, so let's go back to, okay, so there's my picture, and again, it's coming out of the page, and it would look something like that. That's one of these squares. You with me? So how do I integrate all the squares? I'm going to take the integral from the lowest x value to the highest x value. And I'm talking about, just like what we were saying, from here to here. Guys, how am I going to find those a and b values as far as from low to high? Set the equation equal to each other and find the intersections. The x values of those intersections. Let's do that real quick. So I have x plus 1 is equal to x squared minus 1. There's an x squared and an x, so I know it's quadratic. So when I subtract it, it'll look something like this, where you have the x value is -1 and the x value is 2. So we know at -1 to 2 is going to be what we're going to set our integral that we're about to matriculate through that base. Okay? Side squared. That's what we're looking for. Side squared. This is big. Okay? So we know it's side squared dx. And that's it. There's no pi on this one because they're not circles. Can someone tell me what I'm going to do to determine this side right here, the length of that side? Just top minus bottom. Blue equation minus the orange equation. So the top, let's make some more room so it's neat. The top is going to be x plus 1. Now you notice why I was doing the parentheses, because they're not just one letter sometimes. They're equations. The top minus the bottom. And the bottom is the orange equation. Notice that I am writing these functions in terms of what? X. Because I'm integrating in respect to x. And then I will close my parentheses, and I will make sure that I do what right now that a lot of people forget? Dx, but also squaring it, because it's side squared. And guys, whatever you get from that, that's going to be the volume.
8.1 units cubed.
Is that what you got? Can you do it to 3 decimal places real quick? And can someone double check that?
It was just.
It's just 0.811, that's it?
Yeah.
Okay, 8.1 units cubed. Because there were no mention of meters or whatever, feet, right?
So you want us to write like units cubed or units squared on the test?
Say again?
On the test, you want us to write the
Unit squared. If they're meters, write meter squared. If they're feet, write feet, or sorry, cubed.
I'm saying if it doesn't give us.
If it doesn't give you anything, write UN cubed.
And on the AP exam, like say it is just 8.1, would it be best to write the 0, 0?
Either one. If there's zeros, they're negligible. You don't have to. But I will always want you to remember. There's so much things to remember. That's why I'm just trying to be as consistent with things whenever. Okay. So this is if they're squares. Okay. Now you don't want to erase that work. Even on the AP exam, you don't want to just negate it out, because a lot of times, if they're giving you other things, you're going to use that for the other things as well. Okay? So you could have one of these, or you could have a revolution. To me, I think the revolutions are a lot easier to see. These are a little bit different, but they're still, the approach, there's a lot of similarities in the approach. Let's do rectangles with a height of 1. Okay? So rectangles with a height of 1, let's see if I could, yeah, I didn't think it would let me. But if instead of making this a square, I'm going to make it a rectangle. Okay, so I'm going to draw this somewhere else, because right now I have the square going on. And the height is 1. So here we go. First of all, let's draw the base of our rectangle right here. The height is 1. Will the height always be 1? Yep. And now you can see that this is not going to be the same shape, because it doesn't come out as far. The bases are longer than the heights. Okay? So here we go. What's the area formula for a rectangle? Base times height. But I'm going to change one of these letters to a number right now. What's the letter that I'm changing? Height. And the height is going to be 1, because it is a constant. It is always 1. And because it's always 1, plug in the constant right now. It doesn't change, so don't leave it as a variable. Variables change. Okay? So basically we could say the area formula is just whatever we get for B. You with me? So the length of B is right here. Do we already have this? We do. We do already have the length of B. What's the length of B? What's the length of B on this? It's going to be the top minus the bottom. So the top minus the bottom is going to be the blue function, right? Which is x plus 1, minus the bottom, which is the orange function. Notice the parentheses are very important. This whole thing right now, guys, is B. It's very similar to what we did before, but the big part is that I'm not going to do what? I'm not going to square it. I'm just multiplying it by 1. So those of you in the calculator,
4.5 units squared.
say it again one more time.
4.5 units cubed.
Are we good?
So what exactly is 4.5 units? Because it's not the area, or it's not the width of the base of the slice, is it?
It's the volume.
It's the volume. It's the volume of all of these rectangles that would go through that all have the same height of 1.
So
Their just bases are changing.
So we're using the base to find that.
Yeah. So it's all about this. I know that these equations are so easy, but how you use them in calculus, you got to be very methodical with how your approach is. Okay? All right, so now let's do we're not doing semi-ellipses. We'll do equilateral triangles. And then we will finish this off with semicircles. Okay, and this will be our last example, okay? This is a really big video too. So let's do equilateral triangles. Okay, so to make room, I'm going to take all this off. And let's look at what the picture will look like, and then develop the equation. So now, I'm going to do it way over here off to the left, and I'm going going to draw a small little equilateral triangle. So here's the base of it. And then when it comes out of the page, it will look something like the following. So it comes out of the page like this. And then we're going to highlight it so that we can see this cross-sectional area. Okay? What's the equal, and this is an equation you should write down or have somewhere memorized. What's the equation for the area of an equilateral triangle? Side squared times root 3 over 4. Side squared times root 3 over 4 is the area of an equilateral triangle. You with me? Constant multiple rule I've stressed so much because now I have side squared and the root 3 over 4 is pulled out. Okay? So now I'm going to have to figure out what's the length of this side. Guys, we've done this length of the side now 3 times. The length of any side of an equilateral triangle is the top minus the bottom. Whoops, I didn't mean to do that. So the top minus the bottom is going to be basically the blue minus the orange, yet again. And do I square it? Yes. They're all dx's, remember, because they're perpendicular to the x-axis. And yes, I square it. So this looks a lot like the square one. The only difference is we're multiplying it by root 3 over 4. Can you see that? So all of these are very, very close to one another, but give drastic volume differences. Okay? So even a small little square could throw the whole thing off. That's why we have to be very meticulous with our work. Those, what do you get?
3.507 units cubed.
3.507 units cubed. And I appreciate your help on this, Brooks. 3.507?
Yes.
Okay. Now, it's not so bad, right? You're starting to get the hang of this now. And I will end with the one that's a little annoying, the semicircles. Okay? Here we go, the semicircles. Let me draw this one kind of from this rectangle. I'm going to pretend that it's a semicircle just for the sake of time. There's your semicircle. So it's got roundedness to it, if you will. Okay, here we go. Step 1. We got to figure out what's the area formula for a semicircle. What is it? Pi squared over 2. Be methodical. Don't change. Just methodical with your approach. What am I going to pull out? Pi over 2. Because of constant multiple rule. So what I'm looking for is r squared. Now be very careful on this one because a lot of people refer to, oh, it's just the b. It's just the blue minus the orange yet again.
It's b over 2.
But it's the b over 2. So it's the base. Otherwise the r, let me highlight it. This r squared is all here. The pi over 2, guys, this is what most people struggle with. This over 2 already came out. But now I need to find on this semicircle, let me enlarge this semicircle for some of you. Okay, there's the semicircle. My goal, it's highlighted in green, is to find r. Either that one or this one. So how do I find that? I find it by finding the base, which is all of this, and then just divide it by 2. And the base, guys, what's the top? X plus 1, it's the blue function. Minus the bottom, what's the bottom? X squared minus 1. This is the length. If I were to say, hey, this is the base, I'm there right now. But I only want half of this because I'm looking for the radius. So I divide all of this inside of the parentheses before squaring it by 2. And this will will give me the volume of a semicircle. Then what do I get?
3.181 meters cubed.
Excellent job, guys. Now you've had videos with axis of revolutions, and you've had cross-sectional perpendiculars. The only things that we need to practice are the same things, but dy-wise. Give you a little bit, but at least we got a solid, pretty close to solid understanding already approach with all the dx slices. Cool? I really hope the sound recorded on this video.